Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 6, Aircraft Aerodynamic Surfaces and Controls. An aircraft is not useful just because it can generate lift. It must also remain stable, hold a chosen flight condition, respond predictably to commands, and recover from disturbances such as gusts or turbulence. That requires aerodynamic surfaces that do two jobs at once. First, some surfaces provide stability. They help the aircraft resist unwanted changes in attitude or direction. Second, some surfaces provide control. They let a pilot or flight control computer intentionally change the aircraft's attitude and flight path. A conventional airplane does this with its wing, horizontal tail, vertical tail, and movable control surfaces. The best-known primary controls are the elevator, ailerons, and rudder. They control pitch, roll, and yaw, respectively. The FAA and NASA describe the fixed horizontal and vertical stabilizers as the surfaces that provide aircraft stability, with elevators, ailerons, and rudder as the main movable control surfaces. 1-2. This lesson explains those surfaces, how they work, why an aircraft needs more than a wing, and why the systems that move them are as important as the surfaces themselves. The aircraft has 3 rotational motions. Before discussing controls, it helps to identify the 3 ways an aircraft can rotate. An aircraft can move forward, backward, upward, downward, and sideways. Those are translations. It can also rotate around 3 imaginary axes that pass through its center of gravity. The 3 rotations are pitch, nose up or nose down, roll, one wing rising while the other falls, yaw, nose moving left or right. Think of pitch as nodding your head yes. Think of yaw as turning your head left and right. Think of roll as tilting your head toward one shoulder. Each motion has an associated axis. Pitch occurs around the lateral axis, which runs from wingtip to wingtip. Roll occurs around the longitudinal axis, which runs from nose to tail. Yaw occurs around the vertical axis, which runs from top to bottom through the aircraft. The names sound abstract, but the practical point is simple. An airplane has to control all 3. A pilot who wants to climb or descend manages pitch. A pilot who wants to enter a turn rolls the airplane into a bank. A pilot who wants to keep the nose aligned with the direction of travel uses yaw control. These motions are linked. Rolling into a bank changes the direction of lift and initiates a turn. Adding power can create pitch or yaw effects depending on engine placement. Lowering flaps can change both lift and pitching moment. A strong crosswind can produce roll and yaw at the same time. The control system must therefore manage a coupled, moving system rather than 3 isolated hinges. Stability and control are different things. People often use stable and controllable as if they mean the same thing. They do not. Stability is the tendency of an aircraft to respond to a disturbance in a favorable way. Control is the ability to change the aircraft state intentionally. An aircraft that is very stable tends to return toward its original condition after a gust or disturbance. That can make it easy and relaxing to fly. But excessive stability can make it hard to maneuver quickly because the aircraft resists changes in attitude. An aircraft that is highly maneuverable responds quickly to control commands. That can be useful for aerobatics, combat, or unusual missions. But if it has too little stability, it may require constant attention or computer assistance. A well-designed training airplane usually has substantial inherent stability. If a gust tips one wing down, the aircraft tends to resist or slowly return toward level flight. If the pilot releases the controls after a small disturbance, the airplane may settle back toward a stable airspeed and attitude. A modern fighter may be intentionally less stable, sometimes even aerodynamically unstable in a narrow sense, because lower stability can improve maneuverability. A fast digital flight control computer constantly makes tiny control corrections that a human could not make quickly enough. In that case, the computer creates what engineers call artificial stability. The desired balance depends on mission. A long-endurance surveillance drone, a passenger airliner, an acrobatic airplane, and a fighter should not all feel the same in the air. The tail assembly, The empennage. The tail group of a conventional aircraft is called the empennage. It usually includes a horizontal stabilizer, one or two elevators, or an all-moving stabilator, a vertical stabilizer, a rudder, sometimes trim tabs, anti-servo tabs, or other small surfaces. The tail is far from the center of gravity, which gives it leverage. A small force at the tail can create a meaningful turning moment around the center of gravity, just as a small push at the end of a long wrench can turn a bolt. This is the main reason tails are effective. They do not need to be enormous because they act at a long distance from the aircraft's balance point. The tail must work in airflow that has already been affected by the wing, fuselage, engines, and sometimes flaps. It must remain effective through changing speed, angle of attack, side slip, power settings, turbulence, icing, and abnormal conditions. Tail design is therefore not an afterthought. It is one of the main elements that allows an aircraft to be stable, controllable, and recoverable. The horizontal stabilizer. Pitch stability. The horizontal stabilizer is the fixed horizontal surface near the tail. It looks like a small wing. Its primary job is to provide stability in pitch. In plain language, it helps keep the aircraft from pitching uncontrollably nose up or nose down. A conventional airplane's main wing is usually located ahead of the center of gravity, while the horizontal tail sits behind it. The wing's lift and pitching moment, the aircraft's weight distribution, the engine thrust line, and the tail force must all balance. The tail may produce downward force during much of normal flight. This can seem counterintuitive. If the tail pushes downward, does that not make the wing work harder? Yes, in many conventional configurations, the tail does push downward, and the wing must create enough extra lift to support both the aircraft's weight and the tail's downward force. But this arrangement gives the aircraft pitch stability. It is like holding a dart. The heavy point leads, and the fins at the rear keep the dart aligned with its direction of motion. The exact force on the tail can change, depending on aircraft configuration, center of gravity location, speed, flap setting, and trim condition. The tail may produce downward force, upward force, or very little force. The important concept is that the horizontal tail provides a controllable aerodynamic moment that balances and stabilizes the aircraft. If a gust raises the nose, the aircraft's angle of attack increases. A stable aircraft is designed so the resulting aerodynamic changes tend to create a nose-down restoring moment. If a gust lowers the nose, the resulting changes tend to create a nose-up restoring moment. This is longitudinal static stability. It is the initial tendency to oppose a pitch disturbance. The horizontal stabilizer is a major part of achieving it. Elevators. Pitch control. The movable surface on the back of the horizontal stabilizer is the elevator. When the elevator moves, it changes the airflow around the horizontal tail. That changes the tail force, which creates a pitching moment about the center of gravity. In a conventional airplane, pulling the control yoke or stick aft usually moves the elevator upward. An upward elevator deflection changes the tail's aerodynamic loading in a way that generally makes the tail push downward more strongly. The increased downward tail force rotates the nose upward. Pushing the control forward moves the elevator downward and creates the opposite pitch response. The elevator does not directly lift the nose in the same way a person lifts a handle. Instead, it changes the tail's aerodynamic force. The tail then rotates the entire aircraft around its center of gravity. Once the aircraft's nose pitches up, the wing's angle of attack increases. If speed remains adequate and the angle stays below stall, the wing produces more lift. The flight path can curve upward, creating a climb. But pitch and altitude are not the same thing. Pulling back on the elevator initially increases angle of attack and can initiate a climb. If the pilot holds that attitude without adding enough power, the aircraft slows. Eventually, it may stop climbing and could stall. That is why pilot training often uses a useful simplification. Pitch primarily manages airspeed in some flight conditions. Power primarily manages climb or descent in those same conditions. The real relationship is more interconnected than that, but it reminds pilots that elevator commands alone do not create unlimited altitude. Stabilators. An all-moving tail. Some aircraft do not use a fixed horizontal stabilizer plus a separate elevator. Instead, the entire horizontal tail rotates. This is called a stabilator, short for stabilizing elevator. A stabilator is more powerful than a conventional elevator because the entire surface changes angle. It can produce large pitch control forces with relatively small movement. Stabilators are common on many light aircraft, military aircraft, and high-speed aircraft. At high speed, where the airflow is strong and compressibility effects become important, a conventional elevator may lose effectiveness or become structurally difficult to operate. An all-moving surface can remain more effective. Because stabilators are powerful, they often use an anti-servo tab. This small surface moves in the same direction as the stabilator, increasing control force as the pilot moves the control. The goal is to prevent the controls from feeling overly sensitive and to provide the pilot with useful feedback. Some aircraft use a servo tab, which moves opposite the main surface and helps aerodynamic forces move the larger control surface. This reduces the force required from the pilot or actuator. These small surfaces demonstrate an important principle. Flight controls are not only about moving air, they are also about managing control force, feel, stability, and actuator load. The vertical stabilizer. Directional stability. The vertical stabilizer, often called the fin, is the upright fixed surface at the tail. Its primary job is directional stability, helping keep the aircraft's nose pointed into the relative wind rather than allowing it to swing side to side. A useful analogy is a weather vane. The broad tail surface tends to align with the airflow. If a crosswind or disturbance pushes the aircraft into a side slip, the vertical stabilizer experiences airflow from the side. That side force creates a yawing moment that tends to point the nose back into the airflow. This is important because an airplane is not designed to fly efficiently while skidding sideways. Side slip increases drag, changes lift distribution, affects stall behavior, and can make passengers uncomfortable. The vertical stabilizer must be large enough to provide reliable stability and control in difficult conditions, including crosswind takeoffs and landings, engine failures in multi-engine aircraft, turbulence and gusts, high angles of attack, side slip maneuvers, takeoff and landing with flaps or landing gear deployed, propeller torque and asymmetric thrust effects, flight with external stores or unusual payloads. A multi-engine aircraft has a demanding directional control requirement. If one engine fails, the remaining engine produces asymmetric thrust, trying to yaw the aircraft toward the failed engine. The vertical tail and rudder must generate enough opposing force to maintain directional control. That one emergency scenario can strongly influence the size of the vertical tail. Rudder, yaw control. The movable surface on the trailing edge of the vertical stabilizer is the rudder. The rudder controls yaw. When it deflects left or right, it changes the side force on the tail. Because the tail is behind the center of gravity, that side force rotates the nose. In most airplanes, pressing the left rudder pedal deflects the rudder left. The tail is pushed right. The nose yaws left. The rudder is not usually the main control used to make a normal turn. The ailerons bank the aircraft, and the tilted lift vector then creates the turn. The rudder helps coordinate the turn, counter adverse yaw, maintain directional alignment, and manage crosswinds or asymmetric thrust. There are situations where the rudder becomes especially important. Maintaining coordination during turns, countering asymmetric thrust after an engine failure, keeping the aircraft aligned with the runway during crosswind landing, performing intentional side slips, helping recover from a spin, depending on aircraft type and procedure, managing yaw in propeller-driven aircraft, especially at high power and low speed. The rudder's effectiveness depends on airflow. At low speed, the vertical tail has less dynamic pressure and the rudder produces less force. This is one reason why low-speed control can be challenging. A propeller aircraft may retain more rudder authority at low airspeed if the vertical tail sits in propeller slipstream. A jet aircraft's rudder authority depends more directly on forward speed and tail design. Ailerons, roll control. The ailerons are movable surfaces near the outer trailing edges of the wings. They control roll. Unlike elevators, which usually move together, ailerons move in opposite directions. To roll right, the right aileron moves upward. The left aileron moves downward. The right wing produces less lift. The left wing produces more lift. The aircraft rolls right. To roll left, the motion reverses. The ailerons work by changing the local camber and effective angle of attack of the outer wing sections. The downgoing aileron increases local lift, while the upgoing aileron decreases it. Ailerons are located far from the fuselage, because roll control benefits from leverage. A change in force near the wingtip creates a larger rolling moment than the same change in force near the fuselage. But the outer wing is also near the region most vulnerable to tip stall. Ailerons must be designed carefully so they remain effective when the aircraft is slow or at high angle of attack. Wing twist, airfoil selection, aileron size, aileron placement, and stall control devices all affect this. On large aircraft, ailerons may be supplemented by spoilers. At high speed, small outboard aileron deflections can create large structural twisting loads. The aircraft may use inboard ailerons, spoilers, or a combination depending on speed and configuration. Why ailerons can cause adverse yaw. Ailerons create roll by making one wing produce more lift, and the other produce less. but more lift usually comes with more drag. Suppose the pilot commands a left roll. The right aileron rises, reducing lift and drag on the right wing. The left aileron lowers, increasing lift and drag on the left wing. The left wing rises, so the aircraft rolls left as intended, but the extra drag on the left wing pulls that wing backward. The nose may initially yaw right opposite the desired turn direction. This is adverse yaw. It is especially noticeable in aircraft with long wings, at low speed, or when large aileron deflections are used. A pilot coordinates a turn by applying rudder in the direction of the turn, counteracting the unwanted yaw. Aircraft designers also use several methods to reduce adverse yaw. Differential ailerons. With differential ailerons, the upward-moving aileron deflects more than the downward-moving aileron. The goal is to make the drag changes more balanced. The upgoing aileron on the descending wing can add drag by disrupting airflow, while the downgoing aileron on the rising wing is limited to reduce excessive drag. This reduces the tendency for the nose to yaw opposite the turn. FAA-oriented training sources describe differential ailerons as a standard design technique for reducing the drag imbalance that causes adverse yaw. 3. Fries ailerons. A fries aileron is shaped so that when it moves upward, part of its lower surface protrudes into the airflow beneath the wing. This adds drag to the wing with a raised aileron, helping counter the extra drag on the opposite wing. The result is a more balanced yaw response during roll. Spoiler-assisted roll control. Some aircraft use spoilers to assist or replace ailerons at certain speeds. To roll right, the aircraft may raise a spoiler on the right wing. The spoiler disrupts airflow, reducing lift on that wing and adding drag. The right wing drops, and the aircraft rolls right. Spoilers can be particularly useful on large swept-wing aircraft because they reduce the need for large aileron deflections at high speed. They can also avoid some adverse yaw issues because they reduce lift on the descending wing rather than relying entirely on increasing lift on the rising wing. 4. Coordinated flight. Roll and yaw must work together. A well-executed turn is not merely a bank. It is a coordinated combination of roll, yaw, pitch, and power management. When an aircraft banks, the lift vector tilts inward. That inward component of lift turns the aircraft, but the nose must remain aligned with the curved flight path. If the aircraft's nose points too far inside the turn, it is slipping. If it points too far outside the turn, it is skidding. Both conditions mean the aircraft is moving partly sideways through the air. This increases drag and can produce uncomfortable or dangerous handling, especially near stall. A coordinated turn uses aileron to establish bank, rudder to align the aircraft with the direction of travel, elevator to maintain the desired lift and altitude, and power is needed to overcome the added drag. In a small airplane, a pilot often feels coordination through the seat of the pants. In the instrument panel, a small ball in a curved tube, the inclinometer provides a simple indication. Step on the ball is a common training phrase. Press the rudder pedal on the side toward which the ball has moved to restore coordination. In modern fly-by-wire aircraft, computers may automatically coordinate yaw during turns, but the physical principles remain the same. Primary and secondary controls. The elevator, ailerons, and rudder are called primary flight controls because they directly control pitch, roll, and yaw. Other surfaces are called secondary flight controls. They do not replace the primary controls, but they modify lift, drag, trim, or handling characteristics. Common secondary controls include flaps, slats, spoilers, feed brakes, trim tabs, leading edge flaps, variable incidence stabilizers, flaperons, elevens, ruddervators. The exact division between primary and secondary can blur in advanced aircraft. A spoiler can serve as a secondary lift-dumping device during landing, but it can also act as a primary roll control surface. A stabilator is both a stabilizing surface and the main pitch control. Fly-by-wire systems may use many surfaces together to create one desired response. Still, the classification is useful for understanding the traditional aircraft layout. Flaps. More lift and more drag. Flaps are movable surfaces on the trailing edge of the wing, usually inboard of the ailerons. Their main purpose is to increase the wing's lift capability at low speed. As discussed in the previous lesson, flaps increase effective camber and, in some designs, wing area. This lets the aircraft produce more lift at a lower airspeed. Flaps also add drag. That is often useful. During takeoff, aircraft typically use a moderate flap setting. The goal is to improve low-speed lift and reduce runway distance without adding so much drag that climb performance suffers. During landing, aircraft use larger flap deflections. The goal is to fly slowly, maintain a controlled descent, and reduce landing distance. The added drag allows the aircraft to descend at a useful angle without accelerating. Flaps can also create a pitching moment. On many aircraft, extending flaps causes a nose-down tendency because the wing's lift distribution and pressure pattern change. The pilot or flight control system must compensate with elevator or stabilizer trim. This is a recurring theme. Changing one aerodynamic surface affects more than one axis or force. Aircraft behavior is interconnected. Slats and leading-edge devices. Slats are movable leading-edge surfaces. When extended, they create a slot that helps the airflow remain attached to the wing at higher angles of attack. Slats increase maximum lift and delay stall. They are especially important on swept-wing airliners, where low-speed stall behavior would otherwise be demanding. Other leading-edge devices include leading-edge flaps, drooped leading edges, and variable camber systems. All work toward the same broad goal: reshape the wing for low-speed flight. A clean wing is usually best for cruise. A highly cambered, slatted, flapped wing is better for takeoff and landing. Modern aircraft use movable surfaces to become different wings at different phases of flight. Spoilers and speed brakes. A spoiler is a panel on the upper surface of the wing that rises into the airflow. Spoilers reduce lift by disrupting the smooth pressure pattern over the wing. They also add drag. They can be used in several ways: to reduce lift after touchdown so more aircraft weight rests on the wheels, to increase descent rate without excessive speed, to assist roll control, to help slow an aircraft in flight, to manage lift distribution across a wing. When spoilers are used primarily to create drag in flight, they are often called speed brakes. The same physical surface may serve both roles. On landing, ground spoilers deploy rapidly after touchdown. Their job is not just to slow the airplane aerodynamically. By destroying wing lift, they transfer more load to the wheels, making wheel brakes much more effective. Spoilers are especially important on large jet aircraft because they allow rapid lift dumping without requiring the aircraft to wait for speed to decay naturally. Trim. Holding a condition without constant force. A pilot could hold the control yoke or stick in one position for an entire flight, but that would be tiring and imprecise. The aircraft needs a way to maintain a desired attitude or force balance without continuous control pressure. That is the purpose of trim. Trim adjusts the neutral position or aerodynamic loading of a control system, so the aircraft remains in a chosen condition with little or no force required from the pilot. The most common is pitch trim. If an aircraft is flying level at a chosen speed and the pilot must hold back pressure on the controls to maintain that condition, the pilot adjusts trim until the force disappears. The aircraft is then trimmed for that speed, power setting, and configuration. A basic trim system may use a small trim tab on the trailing edge of an elevator. The trim tab moves in a way that creates a force on the elevator, holding it in the required position. Larger aircraft often use a trimmable horizontal stabilizer. Instead of moving only a small tab, the entire stabilizer changes incidence. This provides powerful trim authority and reduces aerodynamic load on the elevators. Trim is not a substitute for active control. If turbulence changes the aircraft's attitude, the pilot or autopilot still needs to correct it. But trim establishes the baseline condition around which those corrections occur. Aircraft may also have rudder trim and aileron trim. These can compensate for asymmetric fuel loading, engine effects, manufacturing differences, or cruise conditions. In an aircraft with autopilot, the trim system is essential. The autopilot uses control surfaces for short-term corrections and trim for longer-term balance. Without trim, the autopilot would have to hold constant actuator force, which is inefficient and can approach system limits. Control authority and control effectiveness. A control surface is useful only if it has enough control authority. That means it can generate enough aerodynamic moment to command the desired aircraft response under the required conditions. Control authority depends on surface area, surface location and leverage relative to the center of gravity, maximum deflection angle, available airflow and dynamic pressure, aircraft speed, air density, the condition of the airflow around the surface, interaction with propellers, engines, wings, and fuselage, structural and actuator limits. At very low speed, controls may be weak because there is little airflow over them. At very high speed, controls may be extremely powerful, but designers may limit deflection to avoid excessive structural loads. A control surface can also become less effective if airflow separates over it. An aileron near a stalled wingtip may not produce the expected roll response. A rudder may be less effective at high angles of attack if it is blanked by the fuselage or horizontal tail. An elevator can be affected by wing wake, flap downwash, or ice. Engineers must make sure the controls work not only in ideal cruise conditions, but also during takeoff, landing, crosswind operations, turbulence, engine failure, stall recovery, and emergency maneuvers. Control surface hinge moments and actuation. A control surface is attached by hinges, but airflow pushes against it. The aerodynamic force trying to rotate the surface around its hinge is called the hinge moment. At low speed, a pilot might move a control surface directly through cables, pulleys, pushrods, or torque tubes. The aerodynamic loads are manageable. At higher speed or on larger aircraft, the hinge moments become too large for direct manual control. The aircraft may need hydraulic actuators, electric actuators, powered control units, or fly-by-wire systems. The actuation system must be strong enough to move the surface against aerodynamic load, reliable enough for safety-critical operation, and designed to avoid unwanted motion or flutter. This is where aerodynamics meets mechanical engineering and systems engineering. A control surface that works beautifully in a wind tunnel is not enough. The aircraft also needs hinges, actuators, sensors, wiring, hydraulics, computers, backups, maintenance access, and failure protections. In some aircraft, the pilot does not move the aerodynamic surface directly at all. The pilot moves a control input device, which sends an electrical signal to a computer. The computer decides how much each surface should move. That is fly-by-wire and multiple surface control. In a traditional aircraft, the pilot's yoke, stick, and pedals are mechanically linked to control surfaces. The relationship is relatively direct. In a fly-by-wire aircraft, the pilot's input becomes an electronic signal. Flight-controlled computers interpret that signal, combine it with sensor data, and command actuators. This allows the aircraft to do several useful things: stabilize an inherently unstable aircraft, automatically coordinate roll and yaw, prevent excessive angle of attack or load factor, limit overspeed or excessive bank angle, compensate for changing fuel balance or configuration, distribute commands among multiple surfaces, detect failed sensors or actuators, reduce pilot workload. A fly-by-wire aircraft may use ailerons, spoilers, elevators, stabilizers, rudders, flaps, and even differential thrust together. The pilot asks for a response such as roll right or climb, and the control system determines the coordinated surface movements. This does not eliminate the need for aerodynamic understanding. It increases it. The computer must know how the aircraft behaves in many conditions, and it must remain safe if sensors, actuators, data links, or parts of the computer system fail. Unconventional control arrangements. Not every aircraft has a conventional tail with elevator, rudder, and ailerons. A tailless or delta-wing aircraft may use elevons, surfaces that combine elevator and aileron functions. When both elevons move together, they control pitch. When they move oppositely, they control roll. A V-tail aircraft may use ruddervators, which combine rudder and elevator functions. Moving both surfaces together produces pitch control. Moving them differentially produces yaw control. A flying wing may use split-drag rudders, spoilers, elevons, or differential thrust because it has no conventional vertical tail. A multirotor drone controls pitch, roll, yaw, and vertical motion by changing the speed of individual motors and propellers. It does not need conventional ailerons, elevators, or rudder surfaces while hovering. These configurations can reduce drag, weight, or radar signature, but they make control system design more complicated. The aircraft must still generate the required forces and moments around all three axes. It simply uses different hardware to do it. A flight example: entering and leaving a turn. Imagine a pilot flying straight and level, then initiating a standard left turn. First, the pilot moves the yoke or stick left. The ailerons deflect in opposite directions. The left wing gains lift or the right wing loses lift, and the aircraft rolls left. At the same time, the pilot applies left rudder to counter adverse yaw and keep the nose aligned with the turn. As the bank develops, the lift vector tilts. Part of the lift now points inward, creating the turn, but less lift remains to support the aircraft against gravity, so the pilot may need a small amount of aft elevator input to increase total lift and maintain altitude. The increased lift and bank also raise drag, so the pilot may need slightly more thruster power to maintain airspeed. To exit the turn, the pilot rolls the wings level with opposite aileron input, coordinates with rudder, relaxes the elevator input, and reduces any added power as appropriate. This one ordinary maneuver uses every primary control surface and demonstrates why aircraft control is coordinated rather than one-dimensional. Key takeaways: aircraft rotate in pitch, roll, and yaw around three axes through the center of gravity. Stability is the tendency to resist or recover from disturbances. Control is the ability to change motion intentionally. The horizontal stabilizer provides pitch stability, while the elevator or stabilator controls pitch. The vertical stabilizer provides directional stability, while the rudder controls yaw. Ailerons control roll by changing lift on opposite wings. Ailerons can create adverse yaw, because the wing producing more lift also tends to produce more drag. Rudder input, differential ailerons, fries ailerons, and spoilers help manage adverse yaw. A coordinated turn requires roll, yaw, pitch, and often power changes. Flaps and slats increase low-speed lift. Spoilers reduce lift and add drag. Trim holds the aircraft in a selected condition without continuous control force. Control authority depends on surface size, location, airflow, speed, density, and actuator capability. Flight control systems range from direct mechanical linkages to powered controls and fly-by-wire computers. Aircraft without conventional tails still need pitch, roll, and yaw control. They simply achieve it with combined surfaces, differential thrust, or other arrangements. The next lesson, 1.7 Real airflow and aerodynamic testing, moves from idealized airflow to the messy reality of boundary layers, turbulence, separation, wind tunnels, measurements, computational models, and flight test validation.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.